Woohoo, we are live. This is Math 75, Mathematical Analysis for Business, and we are in 9.2, which is all about something called continuity. Woohoo! So what the heck is continuity? Basically, continuity is asking the question, are we looking at a function and or a graph that is all put together? Is it all connected? Is it continuous, or is it disjoint and a bunch of just gobbledygook that's just been smashed together and it doesn't quite fit? Continuity is very important so that we can move on to the next step, which is going to be, I know we're all very excited. Godzilla's here because Godzilla is very excited. I know that Spider's very excited, but I'm not sure where he went. Oh no, Spider has lost his stick, but there he is without a stick. We're all very excited because calculus is in 9.3. Woohoo! I mean, technically this is all part of calculus, but the actual derivatives are coming up in the next section. So you guys just got to get through this one last piece of kind of thick theory. So let's talk about the theory. And in fact, I'm going to start with the plain language. In plain language, when a graph can be drawn without lifting your pencil off the paper, so you're drawing it and you're never lifting off, you're always staying on the paper, then that graph is continuous. If there are any jumps or breaks or other sorts of shenanigans, we say that the graph is discontinuous, or some people prefer not continuous. You can use either. So here's the formal definition. Now, this definition is actually really amazing. This is like, there are a lot of holy grails in math, but the goal is to come up with a really densely packed statement. And this is a beautifully densely packed statement. Of course, for students, these are not as much fun, but hopefully I can convince you that this is still kind of interesting. So let's take a look at it. A function f is continuous at a number a if, and then here's the rules. The limit as x approaches a, notice it's a two-sided limit, so coming in from both sides of f of x is f of a. And what this one little tiny cute little statement means is all of this stuff, which is pretty cool. I'm going to move Spider. Come here, Spider. Go over there. Okay. So first off, f of a must exist. So it has to be defined and be finite. So f, if we plug a into the function, we get a number. The right-sided limit of f must exist. The left-sided limit of f must exist, both at a, and they have to agree. So we've got to have the two sides coming in towards each other, and they have to meet in the middle. If we've got the two sides going and they don't meet in the middle, then this is not continuous. See, there's a little jump between the two. We also need, when I bring the two left and right together, the point needs to be right there in the middle. It has to meet at the point. If the point is somewhere else, then we've missed the whole point. See what I did there? I know, I'm hilarious. Okay, so I'm going to move Godzilla. You guys ready? Let's do the actual practical stuff. Dun, dun, dun! Here is a lovely, beautiful, totally stolen graph from the internet. Thank you, internet. And the reason that I like it a lot, first off, I think it's actually kind of pretty. It's certainly very interesting. And it's got a bunch of just weird, unusual things going on. This one function has got it going on in all sorts of ways. So what we're going to go through is we're going to, for different x values, we're just going to talk about, is it continuous? Is it not continuous? Or discontinuous? And there are a lot of different reasons why a function might not be continuous. So I'm going to squish it up a little bit. The up here is just, I'm not sure why they made it so tall, because you don't really need all of that stuff. So I'm going to push that a little bit. And let's talk. X equals -7. Let me see if I can find my ruler. Dun, dun, dun. Can you guys see it? I think you can see that pretty well. So -7, it turns out, is this dotted line. That is where x equals -7. And so I'm going to start off with that one being the yellow. That's this place right there. That's going to be my yellow one. And is that continuous or discontinuous or not continuous? And the answer is, oh my gosh, that's so not continuous. Why is it not continuous? Well, we've got the graph heading down, and it looks like this is heading down towards, well, let's be honest, negative infinity, and this side is going down towards negative infinity. Are they agreeing? Well, in a sort of a way, they're agreeing, but do you see this dotted line? That means there's an asymptote there, which means that they are likely, they don't just stop in the middle and, sorry, I'm gonna do this there, stop in the middle and then just suddenly come together like that. They both, the way it's drawn, go down, 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 down forever. So there's no agreement. And in fact, it looks like f of -7 does not exist. That would be my guess. So that's the reason. There is no point there. And also the limit from the left and the limit from the right are not finite. They're heading down to negative infinity. Okay, next point, x equals 0. And x equals 0 is going to be right there. So that point is actually a pretty boring point. By which I mean a really well-behaved, this point is quite polite. Notice the point exists where we expect it to be. On the left and on the right, the graph continues on in both directions. Everything seems to meet, oh, sorry, I can't do it without paying attention. Everything meets up right there, exactly where you expect it. Nothing weird is happening. This is continuous. Yay, continuity. Woohoo! Okay, x equals 5. Let's go for orange. X equals 5 is this point right here. Dot, 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 dot. I should have used my ruler because you can't quite see it. Okay, so I've got an open point here. Remember that an open point means that on the right, the graph comes up to this point, but it doesn't exist. So this is open. And then this one over here on the left is a closed point. So notice that f of 5, let's see, seems to be, it looks like it's right about 4. I don't know if you guys would agree. 1, 2, 3, 4. It looks like f of 5 is 4 because that's where the point is. But, and the limit as x approaches 5 from the left of f is 4. But the limit as x approaches 5 from the right-hand side, what is that? That's up here. I think that's like 6. So the two sides don't connect. There's a big jump. If there's a jump there, it's not continuous. So this is not continuous. There's a jump. Okay. These two don't agree. Sad face. Okay, so shenanigans. Seriously, shenanigans. Next up, x equals 13. Let's take a look. That's going to be this point right here. Now, this one is slightly better behaved. Notice that there's no jump. The limit as x approaches 13 from the left of f is equal to, let's see, what is that? I think that's equal to 2. What do you guys think? I think that's about even with 2 there. If this is 1, that's 2. Yeah, I think so. And that's also equal to the limit as x approaches 13 from the right. So the limits agree. So what's the problem? But f of 13 appears to be 3. So the two values don't agree. Remember, to be continuous, You have to have the left and the right coming in, and then you have to have the point right there where you expect it. And here, the point has been, for whatever reason, and we don't know why, but the point has been moved up a little bit. That's not continuous. And again, you'd know that because if you tried to draw this, you could draw this part just fine, but could you draw the open point and the closed point without lifting your pencil? And the answer is no, you can't. So this is not continuous. See, there are a lot of reasons something could not be continuous. Okay, let's try a blue one. X equals 18. That's over here. And this one, on the left and the right, the graph comes together, right? Just fine. But if you look carefully, that's an open point. And there's no closed point. So in this case, f of 18 is not defined. So that's DNE. This is not continuous because you need, for a function to be continuous at a point, left and right have to exist, and the point has to be there in the middle. Woohoo! Woohoo! You guys, you're making it through. This is some thick stuff. So, you know, pat yourselves on the back. You guys are doing awesome. Woohoo! Next question. If you're looking at an expression, not the graph, can you tell whether or not it's continuous? And the answer is yeah, usually you can, actually. They are usually, so when things are discontinuous or not continuous, it's usually pretty catastrophic. So you can see it coming 10 miles away. Me with my glasses, maybe, 10 feet away, but you can see it coming. So first question, is f of x equals x squared plus 3x plus 5? So that's a polynomial. That's a quadratic, right? Is it continuous everywhere? And the answer is yes. Polynomials, it's the reason why we study them. They are so polite. They are so good-natured. You can do anything you want. You can move them around. You can take derivatives. It's just lovely. So we study polynomials because they are well-behaved. And one of the parts of being well-behaved is they're continuous. No jumps, no missing points, no jiggity-jaggedy weird things going on. So polynomials, continuous for all values of x. Woohoo! So what are some examples of expressions that are not continuous functions? Well, take a look at this. Where would you guess this is? I'm going to tell you this is not continuous. No, that is absolutely not continuous. So the next question is, could you tell that that is not continuous, that it's discontinuous? Would you be able to see that? And the answer is absolutely. Notice what happens when I try to plug in f of 2. I'm going to get 2 squared minus 2 on top and 2 minus 2 on the bottom. So that's 4 minus 2 over 0, which is 2 over 0. Oh no. And are we given any options? Like, are we told, oh, well, if x is 2, then you should try this other value. So is this a piecewise defined function? And the answer is no. Piecewise defined functions look like this. So sometimes it's equal to one thing and sometimes it's equal to another. So it's defined in pieces. But this one is a situation where this simply doesn't, the function itself is not defined at f of 2. Or sorry, it's not defined at x equals 2. So the answer is no, it's not continuous. Not. And then here's where, mathematicians love shortening things. Frequently we write continuous as CTS, not continuous at x equals 2, or discontinuous at x equals 2. Okay, well, what about this one? Now, this is an interesting situation because this one, f of 2, is 2 squared minus 4 all over 2 minus 2, which is 4 minus 4 over 2 minus 2, which is 0 over 0. Now, you might say to yourself, wait a minute. If something over 0 is a mess, 0 over 0 must be like a super mess. And the answer is yes. You're absolutely right. It's really a disaster, except, so let me write that. Except, notice that f of x can be written, x squared minus 4 can be written as x plus 2, x minus 2. And remember the work that we did with rational expressions and rational functions? And we said, wait a minute, we can cancel this. And so we get x plus 2 for x is not equal to 2. So we can cancel this. And that's interesting. And so you're saying, I know you're thinking to yourself, oh, if you're spending this much time, it must be secretly continuous. And the answer is nope. Nope, it's not continuous. Not continuous at x equals 2, just like the previous one. But this one's kind of cool. And I don't think we're going to get a chance to play with this in this class, but this is something called a removable discontinuity. A removable discontinuity. And if we've got some time, we can go over why. But I'm going to go on right now because I'm at 16 minutes and get to the next problem before I may have lagged. Give me 1 second. I am seeing if I can get you a handy dandy Desmos, which I can. Look at me. I got the Desmos. Ooh, ring light. Okay, so let's take a look at these two. Let's compare and contrast. X squared minus 2 over x minus 2. X squared minus 2 divided by x minus 2. Oops. And that's when we remember, I hadn't planned this out, so I forgot to do it. You have to put your numerator in. Can you guys see? There we go. You have to put your numerator in parentheses or Desmos gets cranky with you. Let's see, x minus 2. So I've got parentheses. Oops. Oh my gosh, you can tell I am a professional. So you can see the parentheses top and bottom to make sure that Desmos understands what we're talking about. So let's talk about, let me set this up on my x-axis. I want to go from 0 all the way up to 6. And on my y-axis, I want to go from negative 10 to 10. Let's just start with that. Okay. And I can, so can you see what's happening when x equals 2 for this first one? Notice that the right-handed limit is going to go way up, and in fact, it'll be positive infinity. And the left-handed limit is going to come down here and be negative infinity. Let me see if I can play with this a little bit. Let's go to negative 1,000 to 1,000. I don't know if this is even going to be viewable. Can you see that? Right there at x equals 2, the right-hand side goes way up and the left-hand side goes way down. So do the two limits agree? And the answer is no, they go like this, like that. They do not meet in the middle. They go like that. Okay. So what happens if, sorry, let me get the ring light out of your eyes. What happens if in this next one I do x squared minus 4? I'm just changing one tiny little thing. Did you see what happened with the graph? Let me change the y-axis going from -4 to 4. There we go. Interesting. This looks like a straight line. I wonder what line it might be. Might it be the line x plus 2? Now, what's happening here is that Desmos doesn't do one thing. There's one thing it does not do, and that is it doesn't draw little open circles. So let me get this. That open circle should be right where x equals 2 right there. There should be an open circle there. So the graph here looked like that. And the graph here, leaving off my x's and y's and getting all excited. You know when you get excited and you just forget to put everything on? Yeah. So this one's going to look like this, and then there'll be a big circle, and that goes like that. Okay, so notice, how are these two different? Well, this is x squared minus 2 on top, and we get this totally, everybody's running in all directions. It's like what happens when it rains in San Francisco, and everyone's like, I don't even know what to do. And this one is what happens when it rains, like in London, which is pretty much Tuesday or Wednesday or Thursday, or perhaps not London anymore, but maybe Seattle. Pick your favorite rainy spot. Everything's fine. Maybe everybody, takes a day to get used to it. But right here, when x equals 2, it's undefined. So why do I take all this time? I've spent almost 10 minutes on this. I'm clearly very excited. And if you're, a typical student, you'd probably be saying, yeah, you're getting real excited about this thing, and I'm not really sure why. And the answer is that you can fix this one. Because the two limits agree, we could just say, hey, why don't we just say that when x equals 2, we'll just end up here at y equals 4. Why don't we just say that? And if we just plug that little hole there, then we've got a function that will cooperate. So that's called a removable discontinuity. I love them. Okay, let's go on. Next up, this is a piecewise defined function. You've seen them before in this class, but we're dealing with them again. And basically, it's like cases. So like if you are someone who likes, this would be if you go and they've got special box lunches for you. And they say, if you're not a vegetarian, then we've got a ham sandwich. But if you are a vegetarian, then we've got some lovely hummus. That's all. It's just different cases. It's different situations. So let's look here. We want f of x to be 1 over x squared when x is not equal to 0. And you could see why. If you try to let x equal 0, it's going to be a mess. But then when x is 0, we let y be 1. So let's take a look at this graph. So I'm just going to cross that off. I'm going to do 1 divided by x squared. Okay, so let's look at this graph. You can see that. Ooh, you guys can't tell, but right down there is the bunny. The bunny has come to say hi. I'm recording this at almost 10 o'clock at night, and the rabbit's like, it's time to go to bed. I want my snuggles. If you're curious, do rabbits need to snuggle before bedtime? The answer is yes. If you're also asking, wait, aren't rabbits actually nocturnal? The answer is yes, but he's kind of gotten used to everything getting quiet at night. So he likes a little snuggle time before we disappear for 8 hours or 4 hours or whatever. Okay, so let's take a look at this graph. This is a really interesting graph. I know I keep claiming everything is really interesting, and y'all are starting to say, I don't know if this is as interesting as you think it is. And I'm going to say it's totally that interesting. Trust me. So This was an attempt to fix a function. So we have, when x is not equal to 0, we've got 1 over x squared, which looks like this. It looks like 2 of these guys, kind of like these, but at least they're in agreement. They're moving, you know, synchronized mathematics. And then someone said, oh, this is a problem. Maybe we should let this point be right there to kind of plug up this hole, because otherwise there was no point at x equals 0. And the answer is, well, that's lovely, dear, but that didn't fix anything. Because when you've got the two sides of the function, the two limits heading up towards infinity, and then you plug up the hole by letting this point be 0, 1, you don't have continuity, because these two are heading, and then all of a sudden they have to jump back to this point. That's not continuous. No, not continuous. At x equals 0. And the reason for that is the two limits don't agree with where the function actually is. So let's look back at this. This one, the two limits didn't agree. This one, the limits agreed, but the point was missing. And this one is the limits agree, they both are heading up there, and the point is there, but the limits and the point where we plugged it don't agree. And in fact, the limits are infinite, so they just go up forever, and that you can't, I mean, you can't draw infinity in your lifetime, so not continuous. Because the limit as x approaches 0 of the function is not equal to the function at 0. That's what you write. Woohoo? Woohoo. Okay. I know you guys are very excited. You're thinking, well, that was lovely, and now we know a bunch of math, but we're really here to learn about economics and business. So what are you going to tell us about that? And the answer is, woohoo, wait till you see what I have for you. Suppose the weekly sales volume in thousands of units for a product is given by this. I simplified this significantly, but let me write it bigger so you can see it better in the video. It's y equals 35 all over p plus 3, the quantity squared, where p is the price in dollars per unit. So this kind of makes sense because p is in the denominator. So as p gets bigger, as the price gets bigger, what's going to happen to the sales volume? It's going to shrink. So that makes sense. The price and sales should be in opposition unless this is a luxury good. With luxury goods, if you raise the price, people want more of them because there's cachet to having them. So it's fancy. Like a Rolex is fancy partly because it's so expensive and everyone knows it's so expensive. Or like my son loves McLarens, the cars. Those start at like $250,000. That's not going to happen. I'm a teacher. Unless he gets a really amazing job, that's not going to happen. And part of the reason why those, Rolex and a McLaren are so exciting, in addition to being possibly very good products, it's the price is high, and that makes people want to buy it because they want to show off. Like, aha, see how much money I have. Usually, however, like in this one, when the price goes up, the sales come down. And if you want to raise sales, what do? If you want to sell more of something, you lower the price. So that's why the p is in the denominator. Okay, so is this function continuous for all values of p? No. What value of p is it discontinuous for? So it is not continuous for p equals -3, right? If the denominator equals 0, then we got a problem, so -3. Is this function continuous at p equals 24? So we take a look at it. We say, is p equal 24 going to be a problem? No. If you're not sure, you are allowed to go ahead and look at the function. So I'm going to go ahead and look at the function. I've got 35 divided by, and here I have to write x, not p, but you get the gist, x plus 3, the quantity squared. And then let's take a look. When x equals 24, where are we? There we are. Do you see anything interesting happening there? I see nothing interesting happening. When x equals 24, it seems to be very well behaved. Do I see anything that could be a problem for 24? No, if I plug in 24, I get 27 squared, whatever that is. Okay, so yeah, I think it is continuous. It seems to be in the graph. I've got the two limits on the left and the right agreeing. I seem to have there are no extra points anywhere. Next question, is this function continuous for all p greater than or equal to 0? Now, here's the question. Why ask that? Why for p is greater than or equal to 0? Let's look back. What is p? P is the price in dollars per unit. Now, I said this is not continuous when p equals -3. Is there a chance that whatever it is you're selling will sell for -$3? And the answer is surprising. I mean, the book and the videos all say, oh, well, that's foolish. There are never prices less than 0. And the answer is there are prices that are less than 0 all the time. All the time, you'll get something for free. And in fact, if you buy something with something else, that'll lower the price. You'll actually get a discount on something else. If you'll buy this, we'll give you a discount on something else. So there are all sorts of interesting shenanigans that happen with pricing. So, but generally speaking, our price is negative. And the answer is no. In general, prices are assumed to be at least 0, which means you're giving it away for free, or greater than 0. And the answer is it continuous? And yes, where's the problem? The problem is at negative. So the function is continuous for all p is greater than or equal to 0. And so there you go. Even though this function is not a continuous function, over the domain we're interested in, over the interval where p is greater than or equal to 0, it is continuous. Does that make sense? So sometimes functions are not continuous, but we don't worry about it because they're not continuous in a place where we're not going to go. If that makes sense. Okay, so what is the domain for this application? Right? We're not really doing anything with the application. We're just talking about domain. And the answer is the domain is that p, and here I looked it up and I double checked it, and the book does take the stance that p would never be 0. Now, between you and me, prices are often 0 because things get given away for free for all sorts of situations. As I'm recording this in November, people are getting ready for Black Friday. You get stuff for free all the time for Black Friday. However, again, the official word from the book is that prices are always going to be greater than 0, not equal to 0. And so is that going to be a problem? And the answer is no, because this is all we have is this p plus 3, the quantity squared in the denominator. That's a problem at -3. As long as p stays positive, we're never going to run into p equals -3. So that is woohoo. So our prices are then, our domain is going to be from 0 to infinity. And of course, infinity is always written with a parenthesis. You guys are awesome. I think this is possibly my longest ever video. And if you're still watching it and you haven't fallen asleep, nicely done. Yay, Godzilla is proud of you. So that's it. That was 9.2, a lot of theory, kind of weird, kind of funky, but in the next section, 9.3, we get to start derivatives. Yay! I'm very excited. I hope you're excited. Have a great day / night / afternoon / twilight zone, whenever it is that you're watching this. And math on, guys, math on.